Hi and welcome to my first video on approximating the area under a curve, which will lead into the application of integration that is to do with finding areas under curves, which has plenty of real life applications and will be quite important for you moving forward. But first we're going to talk about approximating the area under the curve, which is really important later for functions that we can't integrate, but now also for leading into the idea of using integration for this purpose. So here's some information about what we're going to learn. There is some lightboard videos there, but for start with, let's talk about some rectangle methods. So let's say we had this curve, y equals x squared plus 1. And let's say we wanted to work out an approximate area under the curve between 0 and 3. And so you can see I've shaded in pink what that area might look like. But it's got a curve above it, so it's not an easy area to determine. Firstly, it's really important to think, well, I know that the area's got a width of 3, and it's got a height up to 10, but obviously it's not 10, so this whole rectangle here would be 30. But actually it's a lot smaller than that, probably half or less, so we're expecting an area of maybe 10 to 15. It's always good to have an expectation. But let's build something that's called the upper rectangle method. And I'm going to start by doing it with 3 strips, and I'll do this in orange. And to do this process, I might actually just rub out this pink here, just to make it more obvious what's going on. So, in orange, we have 3 upper rectangles. Now we said we're going to split it up into 3 strips, so I'm using 3 rectangles. That's what the 3 strips refers to. And here's my 3 rectangles. They're called upper rectangles because the rectangles are made between 2 bounds, and they take the upper limit of the two bound in each case. So you can see the first rectangle is made between, and I'll use purple here, this bound, and it's taken the upper limit. Second rectangle between this bound, and the third rectangle between this bound and this bound. So we can write our heights on here. The height of this rectangle is 2, the height of this rectangle is 5, and the height of this rectangle is 10. And therefore, in orange, the area approximation will be equal to the area of the small rectangle, which is 1 times 2, plus the area of the middle rectangle, which is 1 times 5, plus the area of the higher rectangle, which is 1 times 10. And that, of course, is equal to 17, and it's units squared. So we've got an approximate area of 17 units squared, but we know for a fact this is an overestimation because we use the upper rectangles method. And we could do the same thing, if I rub this out, with 6 strips. And I'll only do this one twice, and then we'll break down the second one just in one instance. So again, 6 strips would have 1, 2, 3, 4, 5, 6, 7 terminals or endpoints. And in purple we can, actually I'll do this one in green. Here's our heights. We're still using our upper rectangle, but this time we've got 6 strips. So the rectangles we create will be this one here, this one here, 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 and here. So now we have 6 rectangles. And we have to determine the heights of each of these rectangles. The first height is to this point, which is 0.5 squared plus 1. So that's 1.25. The reason why that's 0.5 squared plus 1 is because the function was y equals x squared plus 1. Next one is 1 squared plus 1 is 2. 1.5 squared plus 1 is 3.25. 2 squared plus 1 is 5. 2.5 squared plus 1 is 7.25. And then 3 squared plus 1 is 10. So we've got our heights. And the area approximation for the 6 strips is 0.5 because the width now is not 1. The width is now 0.5 of each rectangle. Whereas earlier in orange, the width was 1. So we get 0.5 times by 1.25, and then we have 0.5 times by 2 plus 0.5 times by 3.25 plus 0.5 times 5 plus 0.5 times 7.25 plus 0.5 times 10. And this approximation, excuse the writing, it's a bit messy. This approximation, when we work all these out, well, it's 0.5 times a lot of things. So let's add up those lots of things. We've got 3.25 doubled is 6.5, plus 5 is 11.5, plus 10 is 21.5, plus 7.25 is 28.75, and divide that by 2 and you get 14.375, and that's units squared again. So we get another approximation. This one is smaller than the first one, but we kind of expected that, because remember the first one was these rectangles. And these rectangles, I've got just this additional space here, which hasn't been counted in the second one. And you can see that increasing the number of strips definitely improves the accuracy. So there's the upper rectangles method, which is nice. Lots of strips, you'll still get an accurate answer. It's always an overestimation in this case, so we're going to avoid using it and see if we can come up with something better. So here's our second example. What about the lower rectangle method? Now I'll do this again, and just to keep it simple, I'll do it just with 3 strips. Okay, obviously 6 strips would be better, but I think it's a fairly trivial case, and I think that once you see this, you'll know it and you'll be fine. So our terminals are going to be 0, 1, 2, and 10, and 3 again, sorry, which has a height of 10. But our lower rectangles method, unlike our upper rectangles method that was like this, and then up to here, and then up to here, our lower rectangle method in light blue uses the lowest height. So there, there, and there. And I think we can all agree that this is actually probably a worse estimate. Oh, no, perhaps not. It's got a bit of a curvature there, so maybe it's a slightly better estimate, but it's not really that good. So we're going to work out these areas and add them together and see how close that gets to what we eventually get to. And so our area is equal to, it's got a width of 1 again. We're just adding up our rectangles. 1 times 1 squared. Oh, so the lower bound is this one, which is just 0 squared plus 1 is 1. 1 squared plus 1 is 2. And 2 squared plus 1 is 5. So that's 1 times 5, and that's equal to 8 units squared. So upper rectangles method gave us 17, definite overestimate. Lower rectangles method gave us 8, definitely an underestimate, but we have 2 estimates now, and it's somewhere between those two. So there's the lower rectangles method. I always love to introduce this one. What about a mid-rectangles method? And you know, depending on where you read, you'll find heaps of different options. This one's not actually in the textbook, so let's talk about that very quickly. What about if I did a mid-rectangles method for 3, and I mark these points, and instead of using the upper bounds, which are in orange, here, here, and here, and instead of using the lower bounds, which are here, and then here for the second one, and here for the third one, what if I use the mid bounds in pink? This one, and this one. Let's have a look at that estimate. So in pink, that would mean that this comes across to here, and then it goes up to here, and then it goes up to here. Now I don't want to ruin the surprise, but whilst this is a lot better, it's still not the best by a fairly long shot. So that's why it doesn't really get dabbled with too much. We talk about the upper and lower rectangles method, a really good intro to this idea, but none of them are really that effective, so we don't eventually use them. But you can see here that this is going to be better, because we have a little bit of an overrun in here, here, and there, but that's counteracted by the fact that we're kind of missing a bit here, here, and here. So it evens itself out a bit. It's not perfect, but it does even itself out a bit. And so the area in this case, the width again is 1, and the area in this case is 1 times, and we're talking about this height, 0.5 squared plus 1, so that's 1 times 1.25 plus 1 times 3.25 plus 1 times 7.25, and that is 4.5, 11.75 units squared. I've almost put centimeters, but we don't know centimeters, so we have to put units squared or just use squared. So 11.75 units squared is our approximation. You know what? We have a look at this diagram. We can see that actually should be quite good. That should be a pretty close approximation. Maybe under, maybe over. We don't have to worry too much about that, but we're pretty happy with it. So there's the mid-rectangles method. And I think that's where I'm going to leave our first video, just talking about the rectangles methods. Hopefully it's made sense to you. This really needs to be able to drop with you and make sense for you to be able to move on to the trapezoidal rule next. Before you watch the trapezoidal rule video though, you might want to have just a look at this diagram and think to yourself, what might the trapezoidal rule be? Because I think you'll be surprised at how easy you can guess it. All the best.